Welcome back, everyone. In part 3, we're going to work on setting up our training batches. So we're going to be using the built-in TF dataset object, and again we'll be using the from tensor slices method. We actually already saw how to do this in the NLP lecture series, so let's go ahead and do a quick review and set up our batches for our GAN. I'm going to head over back to the notebook. Alright, I'm back at the notebook where I left off last time. First thing we need to do is when setting up our batches, we need to decide on a batch size. So I will go ahead and choose a relatively small batch size. Since we're dealing with technically image data, but only with a dense network, we'll slow down our learning training time a little bit and choose a smaller batch size. If you want training to go faster, you can choose a larger batch size. Okay, and then I will say my dataset is equal to only zeros object that we made before. And the reason I'm setting it up this way is so you can optionally try to run something like my data is equal to xtrain. But for now, we'll just operate on zeros. That way we can really tell if our generator is actually generating numbers such as 0 or not. Okay, next thing we're going to do is set up our data set. So to do this, we simply say dataset is equal to tf.data.dataset, and then we call from tensor underscore slices. And then we pass in my data. And then what we're going to do here is we call shuffle. Even though it doesn't matter too much since it's already kind of just random zeros, you should always shuffle just in case. It's in order. And then what we're going to do here is choose a buffer size. The buffer size is just so it doesn't load everything up into memory. We set a limit in case we're dealing with a really large data set. And usually we just choose 1,000. So we'll go ahead and run that. And then what we're going to do is, if you want to just confirm the type of this object, it is a data set, and it has a shuffle data set since we're actually going to shuffle it. And then what we're going to do here is we'll say dataset is equal to dataset, and we'll start setting up the batches for it by saying .batch, and then you pass in the batch size that you wanted, and then we say drop remainder is equal to true. Recall from the actual NLP lecture series that drop remainder just means if those last few items is less than your batch size, we'll go ahead and just drop those. So if I take a look at the size of my batch, it's 32. And then if I take a look at my data set, the shape of it is 5,923. So that means 32. If we try to divide this up into batches of 32, we get a little bit of leftover. We get 185 clean batches with some images left over. And so all drop remainder does is it drops that last remainder. So we get 185 clean batches, each of 32. And for our data set, 185 batches should be more than enough. We're at most going to drop just 32 images. And out of almost 6,000, that's essentially inconsequential. So we can go ahead and feel safe dropping that remainder. And then what we can do here is call prefetch 1. And then we'll just train this for one epoch. After one epoch, we should be able to see it start generating zeros. Okay, so we set up everything for our batch training. Now it's time to actually create our training loop. So if we take a look at the GAN object we created, it's this sequential model, and I can actually call layers off of this. And notice that essentially I get back a list of 2 sequential models, because recall when we created our GAN, it's essentially just a sequential of the generator and discriminator, which ends up being this concatenated list of the generator and discriminator, which means if I call the first item off of this, I can see my first sequential model, and then I can call layers off of this, and then I see the actual layers here of that first sequential model, and then I can do the same for the second one, which is the discriminator, and I can see my discriminator here. So notice my generator starts off dense and then reshapes everything. And what I can also do is then start calling things off like a summary of my generator model versus a summary of my discriminator model. And this is all just to show you that I can access the generator model by itself or the discriminator model by itself by just calling off of these actual layers, since the layers of the GAN are sequential models themselves. So that's all I really want to show here with this .layers. because what I'm going to do is I'm actually going to grab the separate components before we actually start the loop by saying generator, comma, discriminator equals GAN, and I'm essentially unpacking that list of layers. So I'll go ahead, and this is all now going to go in a single cell, but I have GAN.layers here, and I'm grabbing the generator component from it and the discriminator component. And we can see that layers itself, I could just call the actual models itself. All right, so our training loop is going to be a little different here than what we usually do. Typically we just fit, but since we're operating with essentially two distinct phases, what we need to do is say for epoch, in range epochs, in this case we're just training for one. After one epoch we should be able to actually see results that basically make sense. And what we're going to do is print ourselves a little message just to make sure we're running. We'll say currently on epoch, and then we'll print out epoch. We'll do +1, that way we don't start at epoch 0. And so we'll keep I as a little counter. So I is equal to 0. In our case, we'll essentially just run once. And then for every batch in our data set, what we're going to do here is we'll say I is equal to I +1. So we'll be able to run. And then we'll say if I mod 100 is equal to 0, essentially we've done 100 batches, we're going to print out a little message. This is now so we can track on the current batch. So we'll say, let's actually put a little tab here just for spacing. We'll say currently on batch number, and then we'll input I, and then I can actually calculate how many batches by saying of length of my data, and then just do classic division, so 2 forward slashes divided by batch size. This is just for kind of printing out what we're currently on. And let's make sure we spell that right. There we go. Okay, so again, all I'm doing here is I'm just using I as a tracker to essentially count what batch I'm on. And every 100 batches, I'll go ahead and print something out to tell me what batch I'm currently on. Otherwise, we actually won't see any information while this is training. So we can print out that I'm currently on some epoch, and then print out what batch I'm currently on. And if you scroll up again, recall that we should be having 185 batches. Okay, so now we set this up in 2 phases during the training. Let's make sure we close that off. Let's go ahead and hit enter here. So outside of this if statement, I'm going to start off by the discriminator phase. Okay, so first I need to create some random noise. So we'll say TF random normal noise, and the shape of this noise should be equal to the batch size by the coding's size we chose earlier. Recall, coding size is essentially that latent layer that is at the very beginning of what is essentially almost like a decoder that the generator is operating as. Okay, so we have that random noise, and then what we're going to do is we'll generate some numbers based off just noise input. So this is technically the discriminator training phase, but in order to discriminate between real images versus fake images, we have to actually produce some images. So the generator, what it's going to do on this very first run is it's going to try to generate images. So notice what's happening here. All the generator gets to see is this random noise. And then, given that random noise, see if based off this model shape of going from 100 to 150, 784, and then reshaping it to 2828, what it's going to do is, can you actually produce an image? You can imagine that the very first images that it's going to produce are just going to be absolute noise. So it generates some images. Next, what we want to do is we want to concatenate generated images along with real images. So what we'll do here is we'll say X fake versus real. So we have our fake generated images and our real images from our data set. So the way we're going to do this is with a little bit of TensorFlow commands. They look pretty similar to some pandas in NumPy code, but we have concat, which is concatenate. And what I want to do is I need to pass in a list of what I actually want to concatenate together. I want to concatenate together my fake images. Those are the ones that the generator is generating. And on the very first pass, they should be horrible, but hopefully over time they get better. And then what I need to do is I need to actually grab my current X batch. And to make sure this works as far as data types, I actually need to cast the data type to be float 32-bit. So we'll say tf dtypes cast, and I take in my x batch and cast it to float 32-bit, and then we concatenate this along axis is equal to 0. Okay, so all we're doing here is I have these fake generated images, and then I have my real images from x batch, which I'm casting to float 32. That way later on I don't get errors. If you don't cast to float 32, some versions of TensorFlow, also depending on your operating system, will show errors that it can't concatenate things that are different data types. Okay, so we concatenate those guys together. Now I have my fake versus real. Then what I need to do is I need to actually set the target label for them. Essentially, what is the Y for the discriminator? So the discriminator is going to take tf constant. Well, we're going to have the following. We'll say 0.0 times the batch size. Notice that this is a list. So you might recall that if you take a list of a single item and multiply it by some number, it essentially just expands that list. So I'll show you a quick example of that. In case you're not familiar, this is just basic Python, but let's imagine I have that 0.0 and I times it by 10. The result is here 10 of these. Okay, so that's what I'm doing here. I'm just taking all these zeros times that batch size. And then what I'm going to do is I'll then go ahead and say plus. And notice these are just Python lists. These are not NumPy arrays, so I'm not actually adding 0 plus 1 here. I'm just taking my list of zeros, and then I'm essentially joining it or concatenating along with, here we have 1.0 times the batch size. Okay, so what does this actually look like when it's all said and done? Let's go ahead and grab it here. I'm going to grab these guys, and then let's paste this here and see what we actually get. So if I run this, I essentially get a bunch of zeros first, and then a bunch of ones. So does that actually make sense? Well, if we come back here, we'll see that it does, because the zeros should be 0, not true, for the generated images. The ones should be true for the actual real images from the XBatch dataset. And we have to make sure, whoops, this little cursor there should be right here. Whoops, there we go. So it's essentially a list of single list zeros and a list of single ones. So let me copy and paste that. That's why we actually didn't get those brackets correctly. Let's paste that in, run that again, and just to show you what it looks like. So this is essentially what we're using as our labels. So all these zeros correspond to that first batch of generated images. It's 0, they're not real. And then ones here correspond to the real images, the ones that we actually know are true zeros written by a human as ones. And that is going to be joined up with this X fake versus real. So we have those labels now. Next, what we need to do is, in order to get rid of a keras warning, we say discriminator dot trainable. We actually do want the discriminator to be trained here. We'll say it's equal to true. Recall that previously we said it was false, and that was basically to let the GAN compile. So if you have discriminator.trainable is equal to false here, that's only false for this compiling. It doesn't mean you can never train the discriminator again. So that's why we have to essentially reset it as, okay, now it's time to train the discriminator. So we set that to true, and then we say, take my discriminator and then train on batch on that X fake versus real. And then the Y is that Y1 we just created. So this one's actually pretty straightforward for the discriminator training phase. All we're doing is we start off with some random noise, giving that random noise to the generator and telling the generator, given this random noise, produce some images. So what's really interesting here is the generator never actually sees any real MNIST digits images. All it gets to see here is noise being fed into it. And then it creates these generated images. We get those fake images, these generated images, and concatenate them together with the real images from our current X batch, which recall we're getting from that dataset object we created before. Next, we need to actually create labels for these. And we know the first ones, due to our concatenation, are all the fake images. So we say those will all be zeros, since they're not real. and then we assign 1 labels to all the ones that are real. And you do this regardless of how many classes you have, because recall, the discriminator, all it's trying to do is say what is real versus what is fake. And then we have discriminator.trainable is equal to true, and then we're going to go ahead and train on that batch. And now all that's left to do is to train the generator. So for this, we create some random noise again. We'll just say tf.random.normal for random normal noise. And then we'll say shape is equal to the batch size by whatever the encoding size you want in here. So we'll say coding size. So there's our random noise again. Let's go ahead and just label this as train generator. So there's the random noise. And then after that, what we're going to do is we actually, in this phase, what's happening here is the generator is going to start by producing fake images. And then the discriminator, again, tries to guess whether these images are fake or real. However, in phase 2, what is actually happening here, we want the discriminator to believe that these fake images are real. So what we end up doing is we set those targets all equal to 1. So what we do here is we say y2 is equal to tf.constant. And we have this 1.0 times the size of the batch. So say 1.0, and whoops, make sure we have parentheses here. So 1.0 times batch size, parentheses, close that off. And then to avoid an error, we say set discriminator. This is actually really to avoid a warning, not an error. What happens is Keras, if you put your trainable as true and then say trainable is false, Keras will essentially warn you, are you sure you want to do this? Because you compiled it with a false versus true or vice versa. So that's why we're actually doing this. These 2 lines are technically to avoid these warnings. So we have the discriminator now, trainable is equal to false, and then we end up taking the entire GAN, we call train on batches, or train on batch, and we pass in the noise versus y2. So eventually, hopefully, what's going to happen is at the end of all this training, once these epoch loops are done running, we can just take our GAN and then say, based off some noise, go ahead and give me some sort of generated output. Okay, so we'll go ahead and zoom out, and we can see the entire process here. Again, all we're doing is in phase 1, we feed in that Gaussian noise to the generator to produce those fake images, and we're completing that batch by concatenating in an equal number of those real images. And we set the targets accordingly, where 0 corresponds with those fake generated images, and then 1 corresponds to those real images from the batch. Okay, then we train the discriminator on that batch, and then essentially in phase 2, what we're doing is we feed the GAN itself some Gaussian noise. Its generator will start by producing fake images, then the discriminator will try to guess whether or not these images are fake or real. And again, we want, in this phase 2, we want the discriminator to believe that the fake images are real. So we set the y2 targets to 1. All right, so let's go ahead and run this. This is just running for 1 epoch, but as you run this, what you should see is our little batch indicator. And if you want, you can set this smaller, so instead of 100, go ahead and report on every 10 batches or something like that. But we'll go ahead and just let this run, and I'm going to fast forward in time until this is done running. All right, so this is just finished training for me. Now it's time to actually see if the generator component of the GAN can produce something that more or less looks like a 0. So what we first need to do is ask for some noise. We'll say noise is equal to tf random.normal shape is equal to, and then however many fake images you want. Let's go ahead and ask for 10 fake images by the encoding size. So we run that, and if we take a look at our noise, it's basically just 10 by 100. Recall the encoding size was 100. And let's just show what this noise actually looks like. So that's all it is. It's just noise. So given this series of noise, essentially 10 of these series of 100 noise points, pass this into the generator to get some images. We'll say images is equal to the generator being fed in that noise. And now, if I take a look at the shape of my images, it's 10 by 28 by 28. So I have 10 28 by 28 images. Let's grab the first one, see what it looks like. So notice, it has a lot of zeros, which makes sense, but kind of in the middle, hopefully, starts to actually label some data. So let's say plt imshow and see what this visibly looks like. So we run that, and you get something that more or less should have some sort of circular shape. And if you're getting just something that's very, very noisy or totally blank, go ahead and restart your kernel and train for a couple of epochs. Sometimes it's dependent on your hardware. And if you're really just getting a lot of noise or just really bad results, try downloading our notebook and running our notebook directly. We've actually added a little bit of code to set some random seeds for you in our notebook to make sure you get some good results. So what we did here is notice this does kind of look like a donut, so clearly it's learning some kind of zero. Now, you should also notice with your model, it's highly likely you'll encounter this error known as mode collapse. That was the first image it generated. Let's take a look at the second one, image number 1. Notice that it essentially looks exactly the same. And out of this batch of 10 images, you'll notice they all look either exactly the same or extremely similar. You can see that maybe the values are slightly different. So if I take a look at this little green point, that little green point exists here, but the actual value is slightly different. This one's a little brighter. And you can take a look at maybe here, these bottom points, they're in the same coordination or formation, but these happen to have slightly different values. So they are technically different arrays, but they look almost exactly the same. And this is extremely common with generative adversarial networks. And this is known as mode collapse. So what's actually happening here? Well, what happens is the generator's outputs are becoming less diverse. And so what's actually happening is the generator basically figured out that it could produce one single image that would always fool the discriminator. And that single image was essentially something that looks like this. So the generator is starting to think, so to speak, why would it try to bother to learn other types of zeros when it figured out the type of zero that can fool the discriminator? So it gets caught in this feedback loop of consistently producing the same image. And then sometimes this can oscillate as the discriminator gets smart to this image. Suddenly the generator collapses back down to noise and then thinks of another zero it can generate, etc. And it's almost like this cycle of noise versus a single zero, noise versus a single zero, where that single zero is the image it figured out that could fool the discriminator. So there's this kind of weird oscillation that can occur due to this mode collapse. Now, this is essentially state of the art as far as trying to figure out how we can prevent mode collapse. There's a couple of different ways that people can go about it, and I've linked a couple of research papers where researchers are actually trying to do things like propose new cost functions or different techniques to stabilize training or avoid this mode collapse. So things they're actually trying to do is maybe techniques like experience replay, which actually consists of storing the images produced by the generator at each iteration into what they call a replay buffer. And then it gradually drops those older generator images. That way the discriminator gets to see newer stuff and you don't get this kind of repeat image that the generator understands it fools the discriminator. Another thing to notice here is we actually used a completely dense network to produce 2D images. It might make more sense to try to create a convolutional network-based GAN. And these are known as deep convolutional GANs, or DC GANs. So what we're going to do is in the next series of lectures, essentially going to edit our network. So instead of using dense layers, since we're dealing with 2D image information, let's see if we can use convolutional layers. Okay, I hope you found this project really interesting. Again, we're dealing with state-of-the-art stuff here, and it's highly likely that we're not going to be able to produce perfect zeros, but if you were able to produce something that is at least circular in shape, then you know your generator has at least attempted to learn something from the images of zeros. And what's really cool is it never even got to see the images. All it gets to see is noise. I'll see you in the next series of lectures where we begin to discuss deep convolutional GANs.